The modern petrochemical industry operates on a massive scale. To refine crude oil into usable fuels, engineers push enormous volumes of fluid through a labyrinth of pipes and processing tanks. Pharmaceutical manufacturing requires an entirely different, highly sterile environment. Yet the creation of life-saving medicines relies on an identical baseline requirement: absolute chemical purity. Even before you hit that industrial scale, the foundational task of almost every chemistry laboratory is isolating distinct chemical substances from one another. Despite producing vastly different things, all of these industries share a singular dependency. To make their products, they have to extract perfectly isolated substances from their raw environments. The natural world rarely hands us pure substances. Raw resources are almost always densely blended mixtures of many different molecules. This creates an immediate engineering dilemma. You have to physically untangle these complex molecular mixtures without destroying the valuable substances locked inside them. Early scientists discovered that extreme temperature could pull these mixtures apart far more effectively than any mechanical filter or sieve. By applying intense targeted heat, human industry found a reliable mechanism to divide the indivisible. To see how this works, we have to trace the timeline back over 1,000 years to the Islamic Golden Age, a period of massive scientific advancement in the Middle East. During this era, an early chemist named Jabir ibn Hayyan pushed the boundaries of experimental laboratory techniques. His most lasting contribution was developing specialized physical equipment designed expressly to capture, control, and utilize high temperatures. These purpose-built chambers transformed fire from a destructive force into a precise surgical instrument for chemistry. This controlled thermal separation process is called distillation. Distillation starts with heat. When you apply a precise temperature to a mixture, you can target specific substances. This works because different chemicals react and break their physical bonds at completely different thermal thresholds. Once a targeted substance hits its specific boiling point, it undergoes a phase change. It breaks away from the liquid state, rising up and escaping the mixture entirely as a vapor. This phase change is the exact moment of purification. The desired chemical has been successfully isolated from the surrounding noise, but right now it only exists as a fleeting hot gas. That creates a vulnerability. If the chemical remains a vapor, it will simply drift into the atmosphere and be lost completely. That requires a final critical phase: condensation. The equipment physically routes this escaping hot vapor into a cooled environment, stripping away its thermal energy. This forced cooling causes the gas to physically collapse back into a liquid state. The distinct, perfectly purified chemical then drips into a final collection vessel, completing the separation cycle. Over the following centuries, chemistry laboratories continued to evolve, yet they retained this exact same thermal methodology for purification. To meet the demands of modern society, this three-step cycle has been scaled up to massive proportions. These towering industrial columns are giant automated versions of Jabir ibn Hayyan's ancient copper apparatus, performing the exact same physical task. Despite its age, distillation remains one of the single most important and irreplaceable separation techniques in all of contemporary science. The entire industry runs on an inescapable loop: the continuous application of heat, the capture of vapor, and forced condensation. Whether a manufacturer is producing life-saving pharmaceuticals or processing high-octane fuels, they cannot bypass this cycle. Every time a modern industry purifies a chemical, an ancient 1,000-year-old mastery of heat is hiding right behind the process.